Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Glad to be back.
So today, I want you to imagine a microscopic scratch on a piece of stainless steel.
Just a tiny one.
Right. To you, glancing at it on a factory floor, it's just a minor cosmetic blemish.
Yeah, you probably wouldn't even run your fingernail over it.
Exactly. But to a colony of listeria or salmonella, that tiny groove is basically a fortress.
It is a massive canyon to them.
Right. It's this deep canyon where they can just hunker down, multiply, and totally survive. Boiling water, acid baths, and bleach.
Which is a terrifying thought for any design engineer.
It really is.
Yeah.
And that one microscopic scratch hiding in, blind spot of a dairy pump could ultimately lead to a $10 million product recall.
Or worse, honestly.
Yeah, much worse.
Uh.
So today we are stepping into a realm where the standard rules of mechanical design are completely upended.
We have to throw the old playbook out.
Totally. We are doing a specialized masterclass deep dive today, tailored for the incredibly curious engineer.
Because you really have to be curious to get into the weeds on this stuff.
You do. Our mission is to answer the most popular pressing questions engineers asked online about sanitary and bioprocessing equipment design.
And it really is, it's a completely different paradigm.
How so?
Well, if you're designing a standard industrial gearbox, your vectors are, structural load, fatigue life, thermal efficiency.
Maybe some vibration analysis?
Right, maybe vibration. Those are the baselines. But when you step into sanitary design, whether that's for a poultry processing line or a pharmaceutical bioreactor manufacturing injectable drugs, you are suddenly battling an invisible, relentlessly adaptable biological enemy.
It's basically biological warfare on a microscopic scale.
It is. You are designing against time, temperature, water, pH, and nutrients. It's this crazy world where mechanical engineering perfectly intersects with microbiology.
So to guide us through this collision of fields, we have an absolute stack of engineering manuals, guidelines, and specifications on the virtual workbench today.
We brought all the heavy hitters.
We really did. We're looking at the ASME BPE 2024 standard. That's the bioprocessing equipment standard.
The gold standard for biotech.
Exactly. We also have the AMI, the American Meat Institute's 10 Principles of Sanitary Equipment Design.
Which is fantastic for heavy washdown environments.
We are pulling from the EHAKG criteria, the European Hygienic Engineering and Design Group, and we've got specific ASTM material standards as well.
A lot of reading, but it's all vital.
So we are going to give you, the engineer listening right now, everything you need to navigate these common design issues using wise, factual, and truthful principles.
We're really getting into the physics and chemistry of why these strict rules exist.
Right, because the why is the most crucial part of this entire discussion.
It is. The ultimate goal of all these standards isn't just to make equipment look shiny and pretty.
Though it does look nice.
It does, but the goal is to prevent the formation of biofilms.
Let's actually pause right there and define the stakes.
Okay, sure.
What is a biofilm, mechanically speaking? Because I think a lot of people just picture, loose bacteria floating around in milk or medicine.
Yeah, that's a super common misconception. Planktonic bacteria, the free-floating ones, they are actually relatively easy to kill.
You just zap them, right?
Exactly. You hit them with heat or a chemical sanitizer, and their cell walls rupture. Boom. Done.
But bacteria are survivalists.
They are incredibly adaptive. When they find a surface, especially one with a microscopic defect where fluids stagnate, they anchor themselves to it.
Like barnacles on a ship?
Very much like that. And within minutes of anchoring, they start excreting this slimy, glue-like substance called an extracellular polymeric substance, or EPS.
EPS. It sounds like a biological epoxy.
It practically acts like one. Yeah. This EPS matrix weaves together proteins, DNA, and polysaccharides into this three-dimensional microscopic shield.
Wow. So they build their own shelter.
They really do. Once a biofilm matures, it forms complex water channels to bring in nutrients and expel waste.
Wait, it has plumbing.
It has plumbing. It's
right.
Essentially a microscopic city. And the terrifying part for engineers is that this EPS shield is highly resistant to standard cleaning chemicals.
So the normal bleach or acid won't work.
A sanitizer that kills free-floating bacteria in 10 seconds might not penetrate a mature biofilm even after 10 minutes of direct exposure.
Okay, so our mechanical engineering goal shifts drastically here.
Completely shifts.
It's not just about what the equipment does to the product, like mixing or pumping. It is equally about what the equipment prevents from happening.
Exactly. We have to design the physical geometry to deny bacteria any chance to drop anchor and build that city.
And that leads us to the core philosophy of the AMI guidelines eliminating pathogen growth niches.
Yes, the niche is the enemy.
Right. A niche is any location on or inside the equipment that traps product debris and resists the mechanical and chemical energy of the cleaning process.
And you have to remember, bacteria are incredibly small.
How small are we talking?
Typically 1 to 2 micrometers for common foodborne pathogens. To put that in perspective, a human hair is about 70 micrometers thick.
That is wild.
So if you leave a gap, a pit, or a crevice in your machine that is larger than 2 micrometers, you have just built them a permanent residence.
I want to visualize how fluid dynamics plays into this because we rely heavily on clean-in-place or CIP systems to wash these machines automatically.
CIP is the lifeblood of sanitary processing.
Let's talk about the concept of a dead leg in piping.
Oh, dead legs, the classic failure point.
Yeah. Imagine your main process pipeline is a busy high-speed highway.
Okay, I'm picturing it.
The CIP cleaning fluid is this massive street sweeper roaring down that highway at 50 miles an hour.
That's a great way to picture the main turbulent flow. It's got energy.
Now, a dead leg is a blind pipe branch, like a T-fitting where one side is capped off.
Maybe for a future expansion or a pressure gauge or something?
Right. In our analogy, that dead leg is a residential cul-de-sac attached to the highway.
I like where this is going.
The street sweeper is roaring down the main road, but when it passes the cul-de-sac, it can't physically turn around inside it.
No, it's going too fast and the space is too tight.
Exactly. It can't maintain its 50-mile-an-hour velocity. At best, it just kicks a little bit of wind down the dead-end street.
And the physics of fluid dynamics back up your analogy perfectly.
Explain the physics there.
In a piking system, you rely on the mechanical shear force of turbulent fluid to physically rip the bacteria and the soil off the metal walls.
Like scrubbing bubbles, but with pure kinetic energy.
Right. But when the fluid rushes past a dead leg, the velocity of the liquid inside that blind branch drops precipitously.
It just dies out.
It does. You transition from highly energetic, turbulent flow in the main pipe to stagnant, laminar flow, or even completely dead fluid in the branch.
And without that energy,
You lose the mechanical shear force entirely.
and without that sheer force, the chemical cleaners just aren't enough, are they?
Not at all. The debris inevitably settles at the end of the cul-de-sac, the bacteria drop anchor, and the biofilm city goes into full production.
That's a nightmare. That's why the ASME BPE standard is absolutely ruthless about dead legs.
They do not mess around.
They have strict mathematical ratios defining how long a branch can be relative to its diameter before it's considered an illegal dead leg.
The L/D ratio. But it's
Yeah.
not just dead legs, We must analyze every single geometry.
What else are we looking for?
Pits, cracks, recesses, open seams, gaps, lap seams, protruding ledges, inside threads, bolt rivets, and blind spots.
It has quite the list.
And all of these are strictly prohibited.
Let's talk about a lap seam for a second.
Okay, let's unpack that.
Say an engineer designs a tank and decides to just overlap two metal plates and weld the outside seam. What happens on the inside?
You've just created a massive capillary trap.
A capillary trap.
Yeah. If the inside of that overlapping joint isn't fully seal welded, there's a microscopic gap between the two plates.
And fluid loves a tiny gap.
It does. Fluid wicks into that gap through capillary action. The surface tension literally pulls the biological fluid deep into the crevice.
But when you run the CIP cycle, the cleaning velocity is zero inside that crack, right?
Exactly zero. The fluid simply bridges over the gap.
So it just leaves the food right in there.
It becomes a permanent bacterial reservoir that will continually recontaminate every single new batch of product you run.
Looking at the evolution of equipment design in our sources, there's a fascinating historical example of this exact problem.
Oh, the stuffing boxes.
Yes. Older food processing equipment used something called stuffing box packing to seal rotating shafts on pumps and mixers.
It's an old-school mechanical engineering trick.
Right. From a purely traditional mechanical standpoint, it makes total sense. You take a fibrous packing material, stuff it tight around the rotating shaft, and crank down a gland nut to compress it.
And the compression forces the fibers against the shaft and stops the liquid from leaking out. Simple.
Simple, cheap, and an absolute nightmare from a hygienic perspective.
A total disaster. Think about the physical properties of that fibrous packing.
It's a sponge.
It is essentially a dense sponge. Over time, it absorbs the food product, it absorbs water, and it provides a massive porous surface area for bacteria.
Oh, man.
To make matters worse, the friction of the shaft spinning against the packing generates localized heat.
Oh, I didn't even think about the heat. So you're providing them a sponge full of food, keeping it perfectly hydrated, and giving it a nice warm incubation temperature.
It's basically a bioreactor designed to breed pathogens.
Wow.
This is exactly why modern hygienic design has entirely abandoned stuffing boxes in favor of mechanical seals.
But even mechanical seals aren't a silver bullet. I mean, you can't just slap a mechanical seal on a pump and call it sanitary.
Yeah, far from it. A mechanical seal uses two highly polished faces, usually one stationary face attached to the pump housing and one rotating face attached to the shaft.
And they slide against each other.
Yes, they are pressed together by a spring to create a dynamic fluid seal. Because the faces are solid materials like silicon carbide or carbon, they don't absorb product like a fibrous sponge.
So that solves the sponge problem.
It does. However, the architecture around the seal, what we call the seal cavity, must be rigorously engineered.
Because if the cavity is too tight, you run into the dead leg problem all over again.
Exactly. If the clearance between the seal components and the housing is too narrow, the CIP fluid cannot circulate through the cavity with enough velocity.
So you lose the shear force.
Right. You end up trapping toxic, biological, or allergenic residues right behind the seal faces.
And we're back to square one.
The hygienic design criteria require that the seal is installed in an open, flushable configuration. The flow paths must be specifically engineered to wash the mechanical seal components.
Do they ever use dedicated cleaning lines for that?
Absolutely. Sometimes engineers even have to design external flush lines that pipe high-pressure cleaning fluid directly into the seal cavity to ensure it gets scoured.
So it always comes back to flow, shear force, and geometry.
Every single time.
You have to ensure that every single square millimeter of the equipment experiences the required chemical exposure and mechanical friction during the cleaning cycle.
And that transition is crucial because you can have the most beautifully engineered, perfectly flowing, mathematically validated geometry in the world.
But if the material is wrong.
Exactly. If you build it out of a porous, reactive, or corrosive material, you have failed before you even start the pump.
Which takes us right into the metallurgical building blocks of our deep dive.
Let's talk metal.
You can't build a sanitary environment out of a sponge, and you can't build it out of something that dissolves. So what is the next logical step for the engineer when specifying the material of construction, or MOC?
The baseline requirements listed in the standards are incredibly stringent.
What are we looking for?
The operational properties dictate that materials must be inert, non-toxic, non-corrosive, non-reactive, non-contaminating, non-porous, impervious, and durable.
That is a tall order.
But here's the critical context. This is not just about the material being safe for the milk or the meat or the medicine.
Right.
It is about the material surviving the brutal chemical warfare of the cleaning process.
Because we aren't just washing these systems with warm soapy water and a kitchen sponge.
No, we are using industrial chemicals.
The sources list some intense sanitizing agents. We're talking about sporicidal agents, parasitic acid, vaporized hydrogen peroxide gas, or 70% IPA isopropyl alcohol.
Take parasitic acid, for example. It is a highly effective, widely used biocide in the food and beverage industry.
Because it breaks down safely. Right.
Yeah, it breaks down into acetic acid and water, so it's environmentally friendly.
Mm-hmm.
But it is also a powerful, aggressive oxidizer.
So what happens if you use standard steel?
If you use a standard carbon steel or even a low-grade series of stainless steel, the parasitic acid will literally eat the equipment alive at the microscopic level, causing pitting corrosion.
And as we just discussed, a microscopic pit is a brand new pathogen condo. So we have to use the workhorses of the sanitary industry, which the guidelines specify as the 300 series stainless steels.
The absolute bedrock of the industry.
The standards say standard stainless steel shall generally be AISI 300 series or better. Let's talk about the heavy hitters, Type 304 and Type 316 stainless steel.
Okay, 304 and 316.
I know 304 is everywhere. It's the classic 18 to 8 stainless 8% chromium, 8% nickel.
You see it in kitchen sinks, appliances, everywhere.
But when you look at bioprocessing and more aggressive food washdown environments, the standard almost always jumps to 316. What is happening at the atomic level that makes 316 so much better?
The primary difference is the deliberate addition of molybdenum.
Molybdenum.
Type 316 stainless steel includes the addition of 2 to 3% molybdenum, represented on the periodic table as Mo.
It just sounds tough, but what does molybdenum actually do?
Well, to understand molybdenum, we have to understand how stainless steel actually works in the first place.
Okay, let's break that down.
Stainless steel gets its stainless property from chromium. When the chromium in the steel is exposed to oxygen in the atmosphere or in water, it reacts to form a microscopically thin, invisible, passive layer of chromium oxide on the surface of the metal.
So it builds its own shield.
It does. This layer acts as a shield, preventing the underlying iron from oxidizing or basically from rusting.
But that shield isn't invincible.
No. This shield has an absolute arch nemesis, chloride ions.
And chlorides are everywhere in these environments.
Everywhere.
They're in salt for food processing, they're in blood for poultry processing, and they are heavily concentrated in many chemical cleaners.
Yes. Chlorides are incredibly aggressive. They can chemically attack and penetrate that passive chromium oxide layer.
And once they get through,
Once they break through, they attack the iron underneath, causing localized, deep microscopic holes. This is what we call pitting corrosion.
so how does molybdenum stop that from happening?
The addition of 2 to 3% molybdenum in type 316 acts as a chemical reinforcement for the passive layer.
Like rebar in concrete.
That's a great analogy. It significantly enhances the stability of that chromium oxide film against chloride attack. It vastly increases the metal's pitting resistance equivalent number, or PN.
Okay, so PN is the metric for toughness against pitting.
Exactly. So, if you are designing a dairy washdown environment where harsh chloride-based cleaners are used daily, or a meat processing line with high salt content, 304 will pit and rust over time. 316 becomes your baseline necessity.
Okay, so we specify 316, but here's where it gets really interesting, and where a lot of younger engineers make a critical, extremely expensive pitfall.
The welding pitfall.
Yes. The sources explicitly state that if you are going to weld the equipment, you shouldn't just specify 316. You must specify the L designation 316L.
The low-carbon variant.
Right. These low-carbon variants cap the carbon content of the steel at a maximum of 0.03%. Now, I want to push back on this.
Sure.
Why does dropping the carbon from, say, 0.08% down to 0.03% matter so much? It's a tiny, tiny fraction of a percent.
It seems trivial until you introduce the extreme thermodynamics of welding.
Because welding is violent.
Incredibly violent. When you weld stainless steel, you are melting the metal with an electric arc. In the area immediately adjacent to the molten weld puddle, a region known as the heat-affected zone, or HAZ, the solid metal experiences a severe temperature spike.
How hot are we talking?
Usually between 800 and 1500 degrees Fahrenheit in that specific zone.
And what happens to the carbon at that temperature?
At those specific elevated temperatures, carbon and chromium suddenly develop a very strong chemical affinity for each other.
They want to bond.
They do. I like to think of it like a microscopic game of musical chairs.
Okay, I love analogies. Walk me through the musical chairs.
The chromium atoms are supposed to be sitting in their outer layer chairs protecting the iron. But when the heat turns up, the carbon atoms grab the chromium atoms and bond with them, forming structures called chromium carbides at the grain boundaries of the metal's crystalline structure.
Ah, I see. If the carbon steals the chromium can't do its job on the surface.
Exactly. This process is called carbide precipitation, or sensitization. The carbon essentially strips the surrounding metal matrix of its free chromium.
Leaving it defenseless.
Completely defenseless. You create microscopic zones right next to the weld that are now entirely depleted of free chromium. Because they have no chromium, they cannot form the passive chromium oxide layer.
So they're effectively no longer stainless steel.
Right. So when the peracetic acid or the chloride cleaners hit that specific zone next to the weld, the metal just rots away.
Rapid, localized intergranular corrosion.
The weld joint literally rots away at the microscopic level, creating a massive, jagged network of crevices for biofilm to take over.
So how does the 316L fix this?
By specifying 316L where the carbon is strictly capped at 0.03%, you rig the game of musical chairs.
You remove the carbon players.
Exactly. There simply isn't enough carbon available in the alloy to bond with the chromium during the short heat cycle of the welding process. The chromium stays in place within the metal matrix, and the corrosion resistance remains perfectly intact across the weld.
That makes total sense. So 0.03% carbon is the magic limit for weldability in sanitary applications.
It's the absolute hard limit.
But what about situations where even 316L isn't enough? Say we are dealing with a pharmaceutical bioreactor running highly aggressive media, extreme chlorides, or very high temperatures. The sources mention advanced alloys.
Yes, when you push beyond the chemical capabilities of 316L, engineers turn to duplex stainless steels like the widely used 2205 grade.
What makes it duplex? Is it two metals slapped together?
It refers to the physical microstructure of the metal. Standard 316L is an austenitic stainless steel, meaning its atoms are arranged in a face-centered cubic crystal structure.
Okay.
Duplex steels have a mixed microstructure consisting of roughly 50% austenite and 50% ferrite, which is a body-centered cubic structure.
So it's almost like a microscopic plywood, blending two different grain structures together.
That's a fantastic analogy. By blending those two structures, you get significantly higher mechanical strength than 316L and much better resistance to chloride stress corrosion cracking.
And do they use other elements to help?
They do. The sources note that nitrogen is a critical alloying element in these duplex grades. Nitrogen acts as an austenite stabilizer and significantly improves the pitting resistance.
And if 2205 still isn't tough enough, what's the next level?
Then you move up to the superaustenitic grades, or nickel-chromium molybdenum alloys.
The really expensive stuff.
Oh, yeah. You'll often hear these referred to by trade names like Hestalloy or Al6XN. And for the absolute most aggressive, destructive environments where you need total, uncompromising immunity to chloride pitting, you use titanium.
Titanium.
Yeah.
But there is a massive catch there, right?
A huge catch. As you move up that alloy chain from 316L to duplex to Hestalloy to titanium, the machining difficulty, the welding complexity, and the raw material costs increase exponentially.
Welding titanium must be a nightmare.
Titanium welding requires perfect, inert gas shielding, or the metal will literally become brittle and shatter.
Wow. This is always a brutal balance of cost versus performance.
Engineering always is.
Now, we've talked extensively about metals. What about non-metals? Can we use plastics, elastomers, or rubber for seals and gaskets?
Absolutely. Polymers are unavoidable. You need elastomers for O-rings, diaphragm valves, and flexible hoses.
You can't make a flexible hose out of rigid steel.
Right. But the guidelines state that composites and plastics must remain intact without changes in shape, structure, or function through thermal cleaning.
Let's explore that. What happens to a polymer during thermal cleaning?
In bioprocessing, you often run a steam in place or CSIP cycle.
Steam. So very hot.
You pump saturated steam at 121 degrees Celsius, that's 250 degrees Fahrenheit, through the entire system for half an hour to completely sterilize it.
And plastics don't love heat.
Not at all. At that temperature, many standard plastics will soften, warp, or permanently deform. An elastomer gasket might extrude out of its groove or take a compression set, meaning it flattens out and loses its springiness.
And when the system cools down?
That deformed gasket leaves a gap.
Another microscopic condo for the bacteria.
Precisely. The polymers must be thermally stable and chemically compatible with both the bioprocessing fluids and the highly oxidative cleaning agents.
So no degrading.
If peracetic acid makes your rubber gasket brittle and it starts shedding microscopic particles into the product stream, you failed.
And what about coatings? I saw a specific note in the EHADD criteria about plating over base metals.
Plated, painted, or coated surfaces are generally frowned upon for primary food contact surfaces.
Risky?
The risk is just too high. A coating is a mechanical bond, not a metallurgical one. Over time, due to thermal expansion and contraction or mechanical wear, the coating can flake off.
And then you have flakes of paint in the food.
Exactly. Now you have a physical hazard in the product, and you've exposed the underlying metal, creating a jagged contamination niche.
But the standard does allow it in very specific circumstances.
Yes. Yes. If engineering plating is absolutely necessary on a product contact surface, for instance, a hard chrome plating to reduce friction on a specific stainless steel sliding component, the EHADG guidelines mandate a minimum thickness.
What's the number?
The plating must be no less than 0.005 millimeters thick. It has to be robust enough to survive the mechanical friction and chemical wear over the lifespan of the equipment without breaching.
Okay, so let's say we've navigated the metallurgy perfectly.
We've got our 316L.
We've selected 316L stainless steel, we've capped our carbon, and we are ready to build. But having the right bulk material isn't enough. The actual microscopic surface topography of the metal must be fundamentally hostile to microbial attachment.
This brings us to a microscopic battleground.
Because what we see isn't what the bacteria see.
Not at all. This is where human perception completely fails us. To the naked eye or even to the touch, a piece of cold-rolled stainless steel sheet metal might look and feel perfectly smooth.
It looks like a mirror.
But if you put it under an electron microscope, It looks like the Rocky Mountains. It is full of jagged peaks, deep valleys, and overhanging cliffs.
And if the valleys are deep enough, the bacteria simply hide in them.
Exactly. Think back to our fluid dynamics analogy. If you have a deep valley on the surface, the high-velocity boundary layer of the CIP fluid simply flows over the top of the peaks.
It just skims the surface.
Right. The fluid down in the valley remains completely stagnant. The microbes sit safely down in the valley, utterly untouched by the mechanical shear force.
To quantify this mountain range, the engineering world uses a metric called average roughness.
Yes.
The math notation for this is R sub A. Now, I want to make sure we understand what R sub A actually represents mathematically, without sounding like a textbook.
It's relatively straightforward to visualize. If you took that microscopic mountain range and drew a perfectly straight theoretical line right through the middle of it.
Like an average sea level.
Exactly like a sea level. A line where the volume of the peaks of the line equals the volume of the valleys below the line. That's your mean line.
Okay, got it.
R sub A is simply calculating the average height of all those peaks and the average depth of all those valleys relative to that mean line. It gives us a single numerical value for how rough the topography actually is.
And our different source guidelines have surprisingly different acceptable limits for this R sub A value. Let's reconcile them.
They do vary quite a bit based on the industry.
The American Meat Institute, the AMI, requires that product contact surfaces must not exceed 32 microns.
Okay.
However, for non-product contact surfaces like the external frame of the machine, the limit is relaxed to a maximum of 125 microns.
Now, contrast that meat processing standard with the incredibly rigorous ASME bioprocessing equipment standard, the DPE, used in the pharmaceutical and biotech industries.
Which is way tighter.
Much tighter. ASME BPE specifies that metal process contact surfaces should have a surface roughness of 35 microinches R sub A, which converts to 0.89 micrometers or less.
I should stop and push back on that. 32 microns for AMI versus 0.89 micrometers for ASME BPE. That is an astronomical difference in precision. Why is the biotech standard so much more punishing?
It comes down to the margin of error and the nature of the product.
Explain that.
Well, in meat processing, you have biological load inherently present, and you use heavy thermal cooking downstream to manage it. You cook the meat.
Right.
But in bioprocessing, you might be manufacturing highly purified water, cultivating incredibly sensitive mammalian cell cultures, or formulating injectable drugs that go straight into the human bloodstream.
Oh, wow. So there's no cooking step later.
None. The tolerance for endotoxins or bacterial contamination is absolute zero. The surface must be unimaginably pristine.
The BPE standard even dictates the exterior environment of the equipment. It states that if the equipment is sitting in an ISO Class 8 clean room, the exterior non-process contact surfaces of the metal construction should be 48 microinches R sub A, which converts to 1.2 micrometers or less.
Yes, because in a clean room, you can't even have a rough exterior.
Why not? The product isn't touching the outside.
Because a rough exterior can shred wiping cloths during external cleaning, generating particulate matter. Or dust and airborne microbes can settle on the rough exterior frame, turning the outside of the machine into a contamination risk that ruins the clean room's air quality.
That makes sense. So if smoother is undeniably better for cleanability, let me play devil's advocate here.
Go for it.
Why not just polish everything to an absolute flawless mirror finish? Does a continuously smoother surface always guarantee a continuously cleaner surface? Why not mandate an R sub A of 0.01 micrometers for every single component?
It's a highly logical question, but it runs into the brick wall of fluid physics and engineering economics.
Economics always ruins the fun.
It's a classic case of diminishing returns. There is a fascinating graph in our source data that illustrates this beautifully. It charts the survival rate of microorganisms per square centimeter against different surface roughness values at a constant cleaning fluid velocity.
Let's break down that data. The graph sets the cleaning velocity, denoted mathematically as C, equal to 1.5 meters per second.
At a cleaning velocity, C equal to 1.5 meters per second, the survival rate of microorganisms drops dramatically as the R sub I decreases.
Okay, give me some numbers.
If you start with a rough surface, say an R sub I of 2.35 micrometers, after the cleaning cycle is fully complete, you are still left with thousands of viable microorganisms per square centimeter.
Because the valleys are too deep.
Right. The surface is just too rough, the valleys are too deep for that 1.5 meters per second flow to shear the bacteria out.
Then you polish the metal and drop the roughness. The data shows that as you hit an R sub of 0.65, 0.55 or 0.45 micrometers, the microbial retention reduces exponentially.
It plummets.
You drop from thousands of surviving organisms down to less than 10 per square centimeter.
Yes. The difference in hygiene between 2.35 micrometers and 0.65 micrometers is night and day. It is the difference between a massive biofilm outbreak and a clean system.
But what about going even smoother?
However, and this answers your question about demanding a mirror finish, look at what happens to the curve as you keep going. The curve completely flattens out.
It bottoms out.
The difference in cleanability between 0.65 micrometers and 0.45 micrometers is marginal. You are only removing a tiny, almost statistically insignificant fraction more of the bacteria.
But the cost to achieve that slightly smoother finish.
The cost absolutely skyrockets. Moving from a standard mechanical polish of 0.8 micrometers to an ultra-high mirror finish of 0.1 micrometers takes exponentially more time, more specialized abrasives, and highly skilled manual labor.
So it's not worth it.
From a sheer engineering economic standpoint, demanding an R-sub of 0.1 micrometers provides almost zero additional hygienic benefit over 0.5 micrometers, but it might triple or quadruple the fabrication cost of the equipment.
Therefore, the standards aim for that mathematically proven sweet spot.
Smooth enough to exponentially reduce bacterial retention, but practically achievable on a manufacturing floor.
So how do we actually achieve this finish? The sources mentioned mechanical polishing is typically done with 150 grit or finer silicon carbide or aluminum oxide abrasives.
That's the manual way.
You are literally mechanically grinding down those microscopic peaks till the surface averages out. But there's also an advanced chemical technique mentioned: electropolishing.
Electropolishing is practically magic for sanitary design. Instead of grinding the metal, it is an electrochemical process.
How does it work?
You submerge the stainless steel part into a bath of temperature-controlled electrolyte, usually a highly concentrated mixture of sulfuric and phosphoric acids.
Okay, a vat of acid.
Then you connect the part to the positive terminal of a DC power supply, making it the anode. You place a cathode nearby.
And what happens when you turn the power on?
The electrical current flows from the part through the acid to the cathode. As the current leaves the surface of the stainless steel, it literally dissolves the metal atoms into the acid.
But wouldn't that just dissolve it evenly and leave the same rough shape?
Here is the brilliant part. Because of a phenomenon called the Helmholtz double layer in the fluid, the electrical current density is much higher at the microscopic peaks of the surface than down in the valleys.
Oh, wow. So the acid selectively melts away the mountain peaks much faster than it attacks the valleys.
Exactly. It levels the surface microscopically. Furthermore, electropolishing preferentially dissolves iron and nickel, leaving behind a surface that is vastly enriched in pure chromium.
So it actually improves the chemistry, too.
It essentially creates a super thick, highly uniform passive oxide layer. It leaves the surface not just smooth, but incredibly passive and hostile to corrosion.
But as incredible as electropolishing is, the ASME BPE standard issues a very specific warning about a manufacturing defect called interrupted electropolish.
Yes, that's a major issue.
What is the physical mechanism behind an interrupted electropolish?
It's a logistical problem, honestly. Imagine a massive 10,000-gallon bioprocessing tank. You physically cannot dip a tank that large into an acid bath. It won't fit.
So what do?
Fabricators have to electropolish it in zones. They build a localized bath or use a wand tool and polish one section of the tank wall. Then they move the setup and polish the next section.
And the overlap is the problem.
An interrupted electropolish occurs when there is a break in the continuity of the electropolishing conditions, like a change in current density, acid concentration, or temperature at the overlapping boundaries between those zones.
So where zone A and zone B overlap, the chemistry gets confused.
Precisely. It manifests visually as a haze, a cloudiness, or a variance in luster across these overlapping boundaries.
And that matters.
Well, a junior engineer might look at that haze and think, it's just a cosmetic defect. Who cares if it's a little cloudy?
But in bioprocessing,
But in bioprocessing, a variance in luster often indicates a fundamental change in the microscopic surface topography, or a dangerous variance in the thickness of that critical chromium oxide layer.
so the haze is actually a weak spot.
That hazy zone might be susceptible to pitting corrosion or provide just enough texture for microbial attachment. The standards dictate that the finish must be strictly uniform.
Okay, we are really putting the pieces together now. We've got the 316L material, we understand the 0.89 micrometer finish, and we've electropolished the parts.
We have individual pristine components.
Now, we have to join them together to actually build the piping network in the tanks. And this is where the rubber meets the road. Welding.
If there is one place where sanitary designs fail in the field, it is at the welds.
Why are welds so tricky?
Think about what welding actually is. It is an incredibly violent physical process. You are melting two perfectly engineered pieces of metal together with a 10,000-degree electric arc, mixing them into a liquid pool and letting them freeze back into a solid.
Oh, without ruining the finish.
Doing this without destroying the geometry, burning away the metallurgy, or ruining the surface finish requires immense skill and strict adherence to the ASME BPE standards.
I want to introduce an analogy that I think perfectly visualizes the main geometrical rule for sanitary welds, the convex versus concave rule.
Let's hear it.
Let's go back to thinking of our stainless steel piped interior as a road. A convex weld where the weld bead bulges slightly outward, raised up into the inside of the pipe, is like a speed bump on the road.
Okay, a speed bump.
A concave weld, where the weld bead sinks down below the surface of the pipe, is like a pothole.
I love this analogy because the physics translate perfectly.
Right. If it rains on the road, the water flows right off the speed bump. The speed bump might be annoying to drive over, but it doesn't hold water, it sheds it.
But the pothole?
The pothole collects stagnant water, dirt, and debris. When the street sweeper comes by, the brushes skip right over the pothole. The sweeper can't clean inside it.
And that is exactly what happens in the microscopic world inside the pipe. The sanitary welding criteria mandate that welds must be flush or slightly convex.
No potholes allowed?
A concave weld creates a sudden dip in the fluid flow, but it's actually worse than just a dip.
Asshole.
At the edges of that concave pothole, at the toe of the weld where the melted metal meets the base metal, concavity often creates what we call a microtrench.
A microtrench. That sounds like a perfect habitat for our EPS matrix.
It is the ultimate habitat, an undercut or a sharp trench right at the boundary line.
Why are they so bad?
Biofilms thrive in these microtrenches because when the CIP fluid rushes through the pipe at 1.5 meters per second, the fluid boundary layer simply bridges straight over the top of the narrow trench.
The fluid just skips it.
The cleaning solutions flow right over the top without penetrating down into the trench to shear away the bacteria. The bacteria are completely shielded from the velocity. Therefore, concavity is strictly, categorically rejected.
The sources outline some absolute zero-tolerance rules for general welding criteria. Let's run through them.
Okay, rapid fire.
First, welds must be continuous, no gaps. Second, full penetration. Now, we use that term a lot in standard mechanics, but what does full joint penetration mean specifically in the context of sanitary tubing?
Full joint penetration means the molten weld metal extends completely from the outside of the pipe where the welding torch is all the way through the wall thickness to the inside surface, entirely consuming the joint.
What if it doesn't?
If you don't have full penetration, you leave an unfused crack on the inside of the pipe where the two tube ends press together.
Which is a massive dead zone.
That crack is a dark, uncleanable void. Fluid gets in, bacteria grow, and the CIP fluid can never, ever reach them.
Next rule. The welds must be flush ground and seamlessly blended to match that required R-sub, a finish we just talked about.
Seamless is the key word.
And here is a very strict prohibition.
Yeah.
No skip or stitch welds. You can't just weld an inch, leave an inch empty, and weld another inch to save time or limit heat distortion.
Absolutely not. A skip weld leaves overlapping metal surfaces tightly pressed together but not fused.
Capillary action again.
Those unfused gaps will instantly wick biological fluids deep into the seam via capillary action. It creates massive, inaccessible contamination zones. Every single joint in a product contact area must be completely, continuously seal welded.
There's a highly specific term in the ASME BPE definitions that sounds like a serious failure. Lack of fusion after reflow.
Oh yeah, that's a bad day on the shop floor.
What exactly is happening on the shop floor to cause that?
In modern bioprocessing, engineers use orbital autogenous welding for tubing. Autogenous means welding without adding any external filler wire. A computer-controlled machine clamps around the tube and orbits a tungsten electrode around the joint, melting the two tube ends together purely with their own base metal.
Okay, so it's a machine doing it.
Sometimes, due to slight misalignments or heat variations, a single pass doesn't quite fuse the inner diameter perfectly.
So the operator sees a flaw and tries to fix it.
Right. The operator might try to run a second pass, a reflow pass, over the exact same joint to melt it again and fix the inner surface.
And that causes the lack of fusion.
The lack of fusion after reflow is a defect where, even after that second intense heat pass has been made, the original joint has still not been fully consumed. It leaves the weld joint with unfused, jagged edges on the inner surface.
Why is that a problem if they heated it twice?
It's a structural failure, but more importantly, it's an immediate hygienic failure. And what's worse, that second hit cycle severely degrades the metallurgy, risking the carbide precipitation we discussed earlier.
Because they subjected it to the heat zone twice.
Exactly. You're giving the carbon two chances to steal the chromium.
So we have all these incredibly strict rules. But let's look at the reality of a massive bioprocessing plant. You might have thousands of feet of intricate piping networks and literally thousands of welds.
It's a massive scale.
How on earth does a mechanical engineer actually verify that the welders are adhering to this? You can't just cut the stainless steel pipes open to check the inside.
No, you can't cut them open. That is where rigorous inspection and quality assurance protocols take over. The ASME BPE standard details exactly how this inspection is handled mathematically.
How so?
The owner, the inspection contractor, and the engineer must agree to a minimum percentage of process contact welds to be selected for borescopic or direct visual inspection.
Borescopic inspection.
Yeah.
So they're threading a flexible fiber optic camera down the inside of the piping network to look at the inner weld surfaces on a monitor.
Exactly. They run the camera down the tubes, looking for concavity, micro trenches, heat tint, or lack of fusion.
How many do they check?
The standard mandates that they must visually inspect at least 20% of the welds in each system installed.
20%.
They randomly select welds to ensure the welders are forced to maintain consistent quality, because they never know which weld will be checked.
Keeps everyone honest.
Furthermore, the inspector must specifically inspect a representative sample of each welder's first shift of production. You have to qualify the operator and the machine setup before they are allowed to weld the whole plant.
Visual inspection with a camera is one thing, but the ASME BPE procedure qualifications go way deeper than just looking at the physical shape of the weld.
They get into the chemistry.
They actually mandate intense chemical analysis of sample weld coupons to verify the microscopic metallurgy hasn't been compromised by the heat.
Yes, the chemical analysis protocols are fascinating. When you weld stainless steel, the extreme heat can cause the chromium to oxidize on the surface inside the pipe, causing a rainbow-like discoloration known as heat tint.
You see that a lot on motorcycle exhausts.
Right. But in a sanitary pipe, if that heat tint is too severe, it means the passive chromium layer is compromised. The standard requires advanced spectroscopy to check the integrity of that passive layer and the heat-affected zone.
The acronyms in the sources here are intense. We have AES, GDOVS, and XP-SESCA. Instead of just listing them, let's break down the physical mechanisms of how these tests actually work.
Let's do it.
Let's start with AES, Auger Electron Spectroscopy.
These are ultra-high vacuum surface analysis techniques. In AES, you take a sample weld coupon and place it in a vacuum chamber.
Sounds expensive.
Very. You bombard the surface of the weld with a focused beam of high-energy electrons. When these incoming electrons smash into the atoms on the surface of the metal, they knock inner shell electrons out of their orbit.
Like billiard balls.
Exactly. To stabilize, the atom drops an outer shell electron down to fill the hole, and in the process, it ejects another electron, an Auger electron.
And what does that tell us?
By measuring the kinetic energy of those ejected Auger electrons, the sensor can identify exactly which element they came from. It tells you the exact chemical composition of the top few nanometers of the weld.
That is incredible. What about GDOES, Glow Discharge Optical Emission Spectroscopy?
GDOES uses a plasma process. You use argon gas plasma to essentially sputter or sandblast the surface atoms off the metal.
Sandblasting with plasma.
As these atoms are ejected into the plasma, they get excited and emit specific wavelengths of light. The spectrometer reads the light to determine the chemical makeup.
And finally, XPS, X-ray photoelectron spectroscopy, also known as SCA, electron spectroscopy for chemical analysis.
Very similar concept to AES, but instead of shooting electrons at the weld, you bombard it with X-rays.
So X-rays instead of electrons.
Right. The X-rays cause the surface atoms to eject photoelectrons. Again, measuring the energy of these electrons tells you the elemental composition.
Okay, so we are bombarding the weld with X-rays, plasmas, and electron beams. What are these tests actually looking for in the data? What constitutes a pass or fail?
The most powerful feature of these techniques is depth profiling. They don't just read the top surface. They can strip away the metal surface atom by atom and measure the chemistry as they go deeper into the material.
So they get a 3D chemical map.
They do. They look directly at the worst discoloration area in the heat-affected zone. They want to ensure two things. First, that the passive chromium oxide layer is still thick enough. Second, that the ratio of chromium to iron in that oxide layer is high enough to resist corrosion.
And if it fails?
If the depth profile shows that the chromium levels drop too low in the top few nanometers, meaning the heat of the welding destroyed the shield, the weld coupon fails. The welding procedure, the gas shielding, or the amperage must be completely rewritten.
That is an unbelievable level of scrutiny. We are verifying the chemical makeup atom by atom to ensure bacteria can't find a foothold.
It's the only way to be sure.
But we have to move on to the next reality of engineering. As much as we'd like to weld the entire plant into one solid, impenetrable block of 316L stainless steel, that's physically impossible.
You have to take things apart eventually.
Exactly. Equipment needs moving parts. Pumps have impellers. Valves have actuators. The machine needs to be disassembled for maintenance. This brings us to joints, fasteners, and mechanical boundaries.
And every single time you introduce a joint that isn't completely seal welded, you introduce a massive risk of creating a micro crevice.
So how do we handle interference joints?
Take interference joints, for example.
Yeah.
This is where you press fit two parts together tightly without welding, like pressing a bearing housing onto a shaft or inserting a sensor probe into a machined port.
The sources outline specific, unbending rules for interference fits. They must be metal to metal only. No liquid sealants, no epoxies.
None.
I want to push back here. Why not use an industrial epoxy to seal the interference fit? It would fill any microscopic gaps.
Because epoxies and liquid sealants degrade. Over thousands of hours of thermal cycling, heating up to 121 degrees Celsius for SiP, then cooling down to 4 degrees Celsius for process chilling epoxies, will microfracture.
They just can't handle the swing.
They will separate from the metal, creating a microscopic void that you cannot see. Therefore, the standard demands purely mechanical metal-to-metal fits. Furthermore, the standard dictates they must be absolutely free of external shoulders and free of relieved areas.
Let's visualize the geometry there. Why are shoulders and relieved areas a problem?
An external shoulder creates a right-angle ledge on the outside of the joint. If fluid flows past it, the sharp corner creates a low-velocity eddy current like a whirlpool in a river behind a rock or soil deposit.
And a relieves area.
A relieved area, which is a machined undercut behind the press fit to make assembly easier, is significantly worse. If fluid manages to wick past the tight interference fit via capillary action, it pools in that relieved void behind the joint.
And you'd never know it was there.
You can't see it, and the CIP fluid can't wash it. Therefore, the tightness of the interference fit must be completely validated to ensure zero liquid migration. The metal faces must be machined to such tight tolerances and pressed together with such force that not even a water molecule can squeeze between them.
And what about the general structural geometry of the machine framework? The shape of the enclosure itself?
The overarching rule is that geometries must be self-draining. You cannot have flat, horizontal surfaces where water puddles can form. Everything must be sloped.
Gravity has to do the work.
And the internal corners of product contact zones are heavily regulated to ensure sweep.
Right. I noticed an exact geometrical mathematical rule from the AMI standards regarding corners. It states that internal corners and angles must have a smooth and continuous radius of at least 3 millimeters for any angle less than 135 degrees.
Let's unpack the fluid dynamics of that.
Let's visualize why that 3 millimeter radius is absolutely necessary.
If you have a sharp 90-degree internal corner, like the inside corner of a machined square box, and you spray a high-pressure cleaning jet directly at it, the fluid hits the converging walls.
And the energy traps itself.
It creates a massive stagnation point right deep in the vertex of the corner. The kinetic energy of the fluid completely dissipates into pressure before it can scrub the very depth of the angle. Debris packs tightly into that sharp corner.
But with the radius.
By mandating a smooth and continuous radius of at least 3 millimeters, you soften the corner into a curve. The cleaning fluid can smoothly sweep along the curve, maintaining its velocity and its shear force, effectively scouring the entire surface clean without stagnating.
That makes perfect sense. Now let's look at the outside of the equipment. The non-product contact surfaces, the external frame, but still within the heavy washdown environment.
The nuts and bolts of it.
Let's talk about the fasteners. Bolts, nuts, screws. The expert rule here is clear. Avoid exposed threads entirely.
Exposed threads are the ultimate pathogen growth niche.
Why are threads so bad?
Think about the geometry of a standard bolt thread. It is a continuous, spiraling, deep, sharp V-shaped groove. It is physically impossible to reliably clean the root of a threaded surface with an external water spray.
The water just bounces off.
The water hits the top of the threads and deflects. The biofilm will just ride out the entire cleaning cycle deep in the roots of the threads, completely protected.
So how on earth do you bolt two heavy things together? You can't weld everything.
You use highly specialized hygienic fasteners. Instead of standard hex bolts where the threads might stick out past the nut, you use closed-end cap nuts, also known as acorn nuts, which cover the exposed end of the thread with a smooth, polished dome.
And the bolts themselves.
The bolt heads themselves should be hygienic hex bolts.
How does a hygienic hex bolt differ from a regular one from a hardware store?
A regular hex bolt has sharp stamped edges, a flat top, and usually embossed lettering with the manufacturer's grade on the top of the head.
Oh, right, the lettering.
Dirt gathers in the lettering and on the flat top. A hygienic hex bolt has smooth, radiused flanges instead of sharp edges, a domed top so water sheds off it, and absolutely no embossed lettering.
Every little detail matters.
Furthermore, if you are mounting a heavy electrical enclosure or a motor to a machine frame, you do not bolt it flat against the frame. You use hygienic standoffs.
Standoffs, they create an intentional gap between the two surfaces.
Exactly. If you bolt two flat steel plates together, no matter how tight you crank the bolts, you create a microscopic gap between them. Water wicks into that gap, stays wet for days, and breeds bacteria.
So the standoff fixes that.
By using a standoff, a solid cylindrical spacer, you separate the enclosure from the frame by a few inches. This allows the factory washdown spray to easily pass completely behind the enclosure and clean the entire surface of the frame without leaving a blind spot.
The environment these machines live in on the factory floor is just absolutely brutal. The notes from the sources point out that belting materials, for instance, must withstand heating to 71 degrees Celsius for up to 30 minutes during washdown.
That's some serious heat.
That's 160 degrees Fahrenheit just for the conveyor belts. And for the equipment itself, the motors, the sensors, the enclosures, in strict washdown environments, the target is an IP69K rating.
IP69K is currently the highest ingress protection rating available in industrial engineering. It is designed specifically for the food and beverage industry.
Break down the numbers for us.
The 6 in the rating means the enclosure is completely, absolutely dust tight. A vacuum is applied and no dust can enter.
Yeah, the 9K.
The 9K signifies that the equipment can withstand close range, high pressure, high temperature washdown jets.
What are the exact physical parameters of that 9K test? Because it sounds like torture for electronics.
It is torture. The test attacks the equipment with water jets at up to 80 bar of pressure.
80 bar. That is nearly 1,200 psi.
When the water is heated to a scalding 80 degrees Celsius. The nozzle is held just 10 to 15 centimeters away from the equipment, and it blasts the enclosure from multiple specific angles, 0, 30, 60, and 90 degrees, while the equipment is placed on a rotating table.
How does that specific combination of 80 bar and 80 degrees Celsius exploit weaknesses in a mechanical design?
It's a dual attack. The 80 degrees Celsius heat causes the external metal and polymer components to rapidly undergo thermal expansion.
So things start shifting.
If the polymer gasket expands at a different rate than the stainless steel door, it creates a momentary microscopic gap. Then the 80 bar of pressure hits.
And blasts water right through that gap.
1200 psi is enough kinetic energy to force water through that temporary microscopic thermal gap. If your electrical enclosure, your servo motor, or your hygienic bearings can survive that combined thermal and kinetic assault without a single drop of water getting inside, you have achieved true washdown survivability.
Okay, we have designed the perfect system. The CAD blueprints are flawless, the 316L metallurgy is chemically sound, the 3mm sweep radii are perfectly drafted, the autogenous welds are convex, and we are using domed hygienic standoffs.
This is beautiful.
The fabrication is complete. But here is the critical final step of the engineering process: validation.
The proof?
How does the engineer, mathematically, scientifically, and visually, prove to the owner or user that the system is actually cleanable? You can't just point at the CAD model and say, trust me, the math works.
No, in bioprocessing and highly regulated food environments, if it isn't documented and physically validated, it simply didn't happen. You have to prove the design works in physical reality.
How do you do that?
The primary method for proving the cleanability of the internal geometry is CIP validation. And the most common, visually striking way to perform this validation is the riboflavin test.
The riboflavin test.
Yeah.
Riboflavin is just vitamin B2, right? Why are we using vitamin?
Yes, it's vitamin B2. We use it because riboflavin has a very specific, incredibly useful chemical property. It is highly fluorescent under ultraviolet black light.
Oh, interesting.
The protocol is simple to understand, but incredibly revealing of bad engineering. You take a concentrated solution of riboflavin and water, and you aggressively spray it over every single internal surface of the equipment.
You just soak the whole thing.
You coat the massive tank walls, you inject it into the complex diaphragm valves, you run it through the impellers of the pumps. You deliberately, heavily contaminate the entire system with this glowing solution.
And then you run your CIP cycle to try and wash it off.
Exactly. You run your standard clean-in-place protocol, the initial water rinses, the caustic wash to break down proteins, the acid wash to remove minerals, whatever the fully validated cycle is.
And then what?
Once the cycle is completely finished and drained, the rigorous part begins. You tear the equipment down, you unbolt the sanitary flanges, you physically open the valves, you disassemble the pump housings.
Taking it all apart.
You take the entire system apart, piece by piece in a darkened room, and an inspector scans every single component with a high-intensity UV black light.
Let's talk about what the UV light is actually doing at a molecular level.
The UV black light emits ultraviolet photons. If there is even a microscopic trace of riboflavin left on the metal, the riboflavin molecules absorb those UV photons, get excited, and then release that energy as visible light.
So it glows.
It glows intensely. If the design and the CIP fluid dynamics are correct, absolutely zero glowing residue will remain. The metal will look black under the UV light.
But if it's flawed?
But if there is a microcrevice you missed in your CAD design, the UV light will show a bright, glowing yellow-green line where the fluid stagnated. If the mechanical seal isn't flushing properly with turbulent flow, the entire cavity behind the seal will glow like a glow stick.
Even the tiniest spots.
Even the microscopic space inside an O-ring groove must be perfectly dark under the UV light. If any riboflavin remains, it proves the fluid velocity was too low or the geometry is flawed. The design has failed and you have to go back to the drawing board.
Now let me push back heavily on this. The riboflavin test relies entirely on a human being holding a black light, manually scanning complex curved geometries in a dark room.
It does.
Doesn't the human element visual fatigue, missing a tiny spot in the deep shadow, or just user error leave a massive margin for failure? Especially when we were talking about finding microscopic pathogens.
That is an excellent, highly valid critique. Visual inspection is inherently subjective. It is prone to human error, which is exactly why the riboflavin test is necessary, but absolutely not sufficient on its own.
So what else do we do?
It is just the visual baseline to catch the obvious fluid dynamic failures. The ASME BPE standard supplements this with highly specific objective mechanical and integrity tests that remove the subjective human visual element entirely.
What kind of objective tests? How do you test for a microscopic gap without just looking for it?
For instance, to mathematically prove the tightness of those metal-to-metal interference joints we talked about earlier, to guarantee absolute zero liquid migration, you don't just look at them. You perform dye penetrant testing.
How does that work?
You apply a low surface tension, highly visible capillary action dye to one side of the press joint. You let it sit for a specified dwell time, sometimes hours. Then, you spray a white developer powder on the other side of the joint.
And the dye travels through the gap.
The dye is chemically designed to wick into cracks that are physically invisible to the naked eye. If even a microscopic fraction of the dye makes it through the joint, the white developer will instantly pull it out and turn red. If that happens, the interference fit is rejected.
And the sources also mention a whole suite of tests for single-use systems or filtration setups. Things like pressure decay tests, bubble point tests, diffusional flow tests, and water inclusion tests.
Yes, these tests are critical for ensuring the absolute integrity of a physical barrier, like a sterile filter membrane.
Break down the pressure decay test.
Take a pressure decay test, for example. You completely seal off a filter housing, pressurize it with a gas, usually nitrogen, to a very specific elevated level, shut the supply valve, and monitor the pressure gauge over a set period of time.
And wait for a drop.
If the pressure drops even a fraction of a psi, it means gas is escaping through a microscopic leak. And if gas can get out, bacteria can get in.
Explain the bubble point test. The source is highlighted, and it sounds like a fascinating application of physics.
The bubble point test is brilliant applied physics. It is used to validate the exact maximum pore size of a microscopic filter membrane. Let's say you have a filter that is rated to block anything larger than 0.22 micrometers. First, you wet the filter membrane completely with a liquid, usually water or isopropyl alcohol. The liquid gets trapped inside the microscopic pores of the filter by capillary action and surface tension.
The surface tension holds the liquid in the hole like a plug.
Exactly. Then you slowly, steadily increase the gas pressure on the upstream side of the filter. The gas wants to push the liquid out of the pores, but the surface tension resists it.
Until it can't.
The bubble point is the exact minimum gas pressure required to overcome that surface tension and physically force the liquid out of the largest pore in the membrane. When that happens, a steady stream of bubbles suddenly appears in the liquid on the downstream side.
So because surface tension and pore diameter have a strict mathematical relationship, knowing the exact pressure it took to pop the plug tells you the exact size of the hole.
Precisely. By measuring the exact pressure where the continuous bubbles appear, you mathematically definitively prove the maximum pore size of the filter. You prove that the physical barrier is intact and small enough to stop the specific bacteria you are targeting. It removes human visual error completely.
And finally, the sources mention NWP, normalized water permeability, for tangential flow applications. What does that prove?
NWP is essentially a baseline performance metric for cleanability. Before you use a brand new system, you measure exactly how much pure water flows through the clean system at a specific pressure and temperature.
So you establish a baseline.
That flow rate becomes your normalized baseline, your 100% mark. Then you run your sticky, heavy biological product through the system. Afterwards, you run your CIP cleaning cycle.
Check it again.
Once it's clean, you run the NWP test again with pure water. If the flow rate is lower than your baseline, say it's only at 90%, it means your CIP cycle failed to remove all the foulants and the internal channels are still partially clogged.
Oh, that's incredibly smart.
It's a purely mathematical proof of whether your cleaning cycle is actually working.
So it's not just about pointing a blacklight at a tank and hoping it looks clean. It's about combining advanced metallurgy, strict geometry, fluid dynamics, and rigorous objective mathematical testing to create an integrated system that is fundamentally hostile to microbial life.
You are engineering an environment where the laws of physics, chemistry, and thermodynamics work together in perfect harmony to ensure absolute, uncompromising purity.
So considering all of this, what does this mean for the future of sanitary engineering? We have thoroughly explored the atomic structure of 316L stainless steel, the economics of 0.89 micrometer finishes, the fluid dynamics of convex welds, and the extreme physics of validation testing.
We really covered the whole map.
But looking ahead, where is the bioprocessing industry actually moving? Is stainless steel going to be the standard forever?
I will leave you with this final provocative thought to mull over. We have focused incredibly heavily today on the mechanical microlevel, the surface finish of the metal, the precise penetration of the TIG weld, the exact 3 mm geometry of the radius.
The physical shapes.
These are all traditional mechanical solutions to biological problems. But the bioprocessing industry, particularly in pharmaceuticals, is currently undergoing a massive fundamental shift toward single-use disposable polymeric systems.
Really, just throw away plastic.
We are talking about massive, flexible plastic bioreactor bags, hundreds of feet of disposable silicone tubing, and plastic single-use pump heads.
Because if you just throw the entire system away after one single batch, you completely eliminate the need for CIP, SIP, and all that exhaustive cleaning validation we just spent the last hour talking about.
You don't have to worry about cleaning a dead leg if you just throw the dead leg in the trash.
That is wild.
Exactly. You bypass the mechanical geometry problem entirely. But as engineers, we know that you never truly eliminate a problem. You just trade it for a new one.
So what's the new problem?
As we move away from stainless steel and toward polymers, how will the physical and chemical principles of leachables and extractables shift the engineering focus?
What are leachables and extractables?
Extractables are chemical compounds that can be forced out of a plastic under extreme testing, and leachables are compounds that naturally migrate out of the plastic and into the pharmaceutical product over time.
So instead of worrying about bacteria hiding in a scratch, you have to worry about plasticizers or adhesives slowly dissolving into the vaccine.
Precisely. We are moving from the mechanical geometry of stainless steel back to the raw chemical stability of polymers. The engineering battleground is shifting from the physical topography of the surface to the molecular structure of the plastic itself.
That is a whole different ballgame.
How do we engineer flexible polymers that can withstand biological loads without leaching endocrine disruptors or toxic compounds into the final drug? That is the next great frontier for the curious engineer.
That is a phenomenal pivot to think about. The physics of hygiene are always evolving, and the problems just keep getting smaller and more complex. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.